Here, let's look at this screen and let me go over how to interpret results for binary regression models. Well, if you recall, last time we learned how to interpret raw coefficients from binary regression estimation. And I said that, well, we can do it, but the challenge would be, the problem would be these raw coefficients here. They're not substantive meaningful very much. Here we use a different model, so the response variable is happiness, with with happiness coded as 1 and unhappiness coded as 0. So a positive coefficient here. So here I already ran the model. I use glm command with this family binomial and logit link to run this model. And the covariates include age, female, black, other, education, income, measure on $1,000. And here also we have this female binary variable to measure gender. And we have two dummy variables, black and other, to measure the effects of race, with whites used as the reference category. Of course, we have age measured on a scale of years. So after running this line, it's a little bit wrapped up, and then we can run summary my logit. So here, my logit is this object name representing the estimation, binary regression estimation results. Now what we'll get is this table below, right? This table below. And as we discussed in our previous video, a positive coefficient here, for example, female or education, increases the odds or likelihood for y to be 1. In this case would be, what is y to be 1? That's happy, right? And a negative coefficient increases the odds or likelihood or propensity being unhappy, etc., etc. But such interpretation is not very substantively very meaningful. Why? Because we don't know exactly the scale or the unit of this response variable, right? The only thing we can talk about is propensity or likelihood, to be very precise. Or sometimes we call that logit. But what is the meaning of that? Not exactly. So how to go substantive? How to provide substantive interpretation of such results? Well, we have to turn to what is called odds ratio coefficients. So how to produce odds ratio coefficients? We're going to take exponential function of these raw coefficients. So we're going to exponentiate the coefficients in this estimation object, my logit. Okay? Exponentiate these coefficients by applying this exp function. Then what it does is it's going to exponentiate all these estimates we see here in this row here. And this is, we can run it, and then we get the results. So how to provide interpretation for such a results? Let me take each coefficient at a time. So for age, we're going to say, well, holding all other variables constant, because in the class I already demonstrate why we need to say holding all other variables constant, because that effect is net of the effects of all other covariates. All the effects of all the, other covariates or coefficients or covariates, they'll cancel out. The only thing left over for the effect of this covariate, that is age on the binary response variable, is the coefficient per se and exponentiated coefficient per se. So let's take this number as an example, which is exponentiated exponentiated coefficient of which number? Of this number. So you can try exponentiate this number, and it's going to become 0.9961298. So how to interpret? We're going to say, well, holding all other variables constant, a net of effects of all other covariates, or ceteris paribus, that's a Latin word for partialing out of all the effects of other covariates. We would expect the odds of y equal to 1, that is being happy, is going to what? Increase or decrease? Well, here is a decrease. Why? Because what we're talking about is factor change. And for factor change, any number bound between 0 and 1, that's going to decrease. Because if you multiply a number which is bound between 0 and 1, and the result going to be reduced, right? Absolute magnitude, right? So here we're going to say, well, holding all other variables constant for each year increase, each unit change increase in age, we would expect the odds of being happy is going to decrease by a factor of 0.9961298. So let's pick female as another example. Again, we're going to say, well, holding all other variables constant, a net of effects of all other covariates, being female as opposed to being male is going to what? Increase or decrease? Here, we're going to say increase. Why? This is a factor change. So for any factor change with its magnitude greater than 1, then that's an increase. So here we're going to say, well, being female as opposed to being male is going to increase the odds of being happy by a factor of 1.1480112. Next one is a little bit tricky because we're going to talk about effects of race as a group, right? Because black and other, both variables measure race. And here we omit white, which is used as a reference category. So here, I'm going to just take black as an example. Again, we're going to say holding all other variables constant, being black versus, well, the omitted category Y is used as a reference category, right? So we're going to say being black versus white is going to what? Decrease the odds. The odds, you have to say odds. The odds of Y being 1. So what is Y being 1? That is happy. So the odds of being happy by a factor of 0.5107743. Okay? So let me repeat again. Holding all other variables constant, being black versus white is going to decrease the odds of being happy by a factor of 0.5107743. So let me talk about education. Holding all other variables constant, a net of the effects of all other covariates for each year increase in this variable, education. Okay, for each unit increase in this variable. So what is that unit in education? Well, this is education. So what is that unit? 1 unit, 1 year. So here we're going to say for each year increase in education, we'd expect the odds, again, is odds, always the odds, when we use odds ratio coefficients. The odds of being happy, y equal to 1, right, is going to increase by a factor, 1.0407627. So let's move on to income. Holding all other variables constant for each $1,000 increase in income, because it's measured on $1,000, we would expect the odds of being happy is going to increase. Why? Because the coefficient is greater than 1. So all odds ratio coefficients are positive, but there's a difference between a positive number bound between 0 and 1, and a positive number bound between 1 and positive infinity. So any number, any odds ratio coefficient between 0 and 1, that's a decrease. Okay, because factor change, multiply something by a number between 0 and 1, that's decrease. And if that number is greater than 1, that's an increase. So again, in this case, let me repeat. Holding all other variables constant on net of the effects of all other covariates for each $1,000. So for each unit increasing x, what is that unit? $1,000 in income. We would expect the odds of being happy is going to increase. Why increase? The odds ratio coefficient is greater than 1. is going to increase by a factor of 1.02222541. So when we talk about odds, the odds of what? Almost always we're going to say the odds of y equal to 1. So here, y equal to 1 is happy. Okay, so we're going to say it's going to increase the odds of y, the odds of being happy by that amount.